So today I'm going to talk about eigenvalue problems in computational physics. So this will mostly be a math, numerical, linear algebra talk, but at bits and pieces throughout it I'm going to sprinkle some physics background just to make sure we're on the same page. And actually I'm going to start with some very, very basic physics that kind of motivates the problem. So if you take any physics 101 undergrad course, they'll talk about the 4 fundamental forces in physics, right? So any force in physics is made up of gravity, electromagnetism, and the strong and weak nuclear force. And what I'm positing today, which is not it's been known for a long time, is basically these forces, decay spatially. That has a lot of important features, but in terms of linear algebra, what that means is that we can often approximate these forces using low-rank matrices or hierarchies of low-rank matrices. As a specific example, if we look at the, so this is just stolen from hyperphysics. If we look at the electromagnetic force, we see it's a power law. It's 1 over the distance squared. So that means if we have, two lumps of particles that are very far away from each other, the electromagnetic force is going to be very, very small. And something you do a lot of if you take these intro physics classes is you learn different ways of approximating forces between charges between particles, things like dipole moments. These are really good and help you cut down a lot of computation, but it's ultimately an approximation. But there was a huge, huge, huge result in the 1980s by Leslie Greengard and Vladimir Rocklin. I know we've had a PUNLAG talk about it before, the fast multiple method. And that's saying when you have 2 sets of particles that are far apart, you can do less work, but you don't even have to approximate it. Because of the low rank property, you can actually look at the matrix. So basically, in terms of numerical linear algebra, this computation is just a matrix vector product. That's all you have to do these charge interactions. And basically, you take the matrix and you analytically, do a Taylor expansion of the kernel of the matrix. And then we are taught in our intro numerical linear algebra classes, matrix vector product is O(n) squared operations, scales with the number of entries. You actually only have to do on the order n log n entries, or if you do it cleverly and have the right kernel matrix, only order n. So this has been, this was a huge, huge result. I mean, Leslie Greengard and Vladimir Rocklin both got very famous because of this. I mean, they've done lots of good work since, but that was their big thing. And it, started this huge revolution in computational physics and even in numerical linear algebra. There's so many algorithms that take this fast multiple method as their, how it got started. The one problem, though, is it's not a strictly algebraic way of thinking. The fast multiple method, all it does is these matrix vector products. It doesn't really consider how to invert matrices and do products of matrices and things. So it has its limitations, and obviously that is important because in computational physics, not everything is just a matrix vector product. We have to solve systems, we need eigenvalues, we need functions and matrices, there's lots of things to do. But since the 1980s, there have been lots of generalizations of this. And so today I'm going to talk about H matrices and HSS matrices, which are some of the most important generalizations of these and how they can be applied to problems in physics. But this is kind of the idea where we get it from. So particularly when we talk about eigenvalue problems, because that's what I do my research in largely. So this is an example, finding the frequencies of an airplane on a shaker table. And they come up everywhere in physics. I mean, there's so many eigenvalue problems in physics, and a lot of them are huge, and a lot of them have this natural low-rank structure. Something you guys I'm sure are familiar with, but everyone, if you're trying to find good computational physics papers about eigenvalues, a lot of them don't even have the word eigen anywhere in them. So a lot of times there'll be papers that just use the word frequency and mode for eigenvalues and eigenvectors, or if some of the quantum mechanics, numerical relativity people use characteristics and rotation. So there's little slightly language differences, but it's all talking about the same thing. So HSS matrices, which I will define formally and give an example over the next few slides, but it's really interesting where it comes from. So there's really kind of 4 different communities of computational science that made big contributions to this. And I would posit the most important is from the computational physics community was the fast multiple method of Greengard and Rocklin. And so that's really cool that now we're using that to solve 2018's cutting edge physics problems. But also there were big contributions from the numerical linear algebra community, particularly rank revealing QR decompositions. And then the fast PDE solver community gave us things like, if you're familiar with multifrontal method nested dissection, that's key to HSS. And then from the control systems community, Shiv Chandrasekaran, who is the inventor of the HSS matrix, was using algorithms like sequential semi-separable matrices. So that's kind of the things that came together to give us things like HSS and H matrices, which is the current state of the art for if we have low rank matrices. So like I said, we have lots of eigenvalue problems in physics. And why do I care that it has this structure? Because that means we can solve it really fast. It's as simple as that. If you have an HSS matrix, so if you have a matrix from physics that has this HSS structure, and I'm going to try and prove to you over the next 40 minutes that a lot of them do, we can get all the eigenvalues, all n eigenvalues, and all n eigenvectors in near linear time. And basically, if it's an n by n matrix, you only need on the order of n operations to get all the eigenvalues and all the eigenvectors. You may say to me, that's ridiculous, an eigenvector is an n by n matrix. But in HSS matrix, you can get its eigenvectors in a tree form. So you can basically get generators that can produce it. So, so yeah, you basically get all the information of an eigendecomposition in only linear time. Linear storage, so that's a huge thing. That's why this is used so much in the computational physics and computational engineering community. So my talk today kind of has two parts. The first, this is just the introduction. The first part I'm going to talk about why physics problems have this structure and how we exploit it and get fast algorithms, kind of for just normal standard vanilla eigenvalue problems. But if you really dive into the literature, most problems in computational physics, especially the ones people care about, are not nice. You don't just get this nice symmetric matrix AX equals lambda X solved for the eigenvalues. That actually doesn't happen very often. More often than not, you might have some non-symmetric matrix, some ill-conditioned matrix. You might have a generalized eigenvalue problem, a nonlinear eigenvalue problem. You might have, well, banded matrix, that's actually a nice structure, but you might have like weird banded structure or some very strange sparsity pattern. You might have high dimensional data. You might have like clustered eigenvalues, make it, so when your eigenvalues are really tight together, but they're different, that makes it very hard to preserve stability. And you might just you might have a physics problem that doesn't scream eigenvalue problem at it. You might have to do some transformations to the problem to get it looking like an eigenvalue problem. So the second part of my talk is I'm going to give a little survey, go through 8 of kind of really important in 2018 computational physics problems, and how we can take our basic algorithm, play some tricks, and apply that and solve these harder, newer problems. So this is kind of the outline of the second part of the talk. This is actually taken straight from, we have a paper coming out in the SIAM review, where it's a long 60-page paper, but one of the sections is on these eigenvalue solvers me and my advisor wrote, and one section 4, is on the physics applications in particular. And so basically it's kind of cool with each of so these are the applications we'll talk about today, from quantum mechanics down to astrophysics and things in between. Basically with every application I highlight some feature or some kind of change to the algorithm you need to do to solve that problem. So it kind of shows you all the Swiss Army knife features of this. Okay, so now for part 1, talking about these hierarchical matrices and why they're helpful for physics problems. So I told you the fast multiple method by itself can only do matrix vector multiplications. The first real generalization of this to a full matrix algebra was by Wolfgang Hackbusch, who's at Germany, huge guy in numerical algebra. In addition to this, he also was one of the pioneers of multigrid. So he has a number of huge results. So his big thing was he took these low rank structures and turned them into a matrix algebra, meaning we can invert, we can add, we can do all these different calculations and do a stability analysis and really formalize it all. So before I get to the formal definition of an H matrix, I want to review with a singular value decomposition and numerical rank. The first one I'm sure you're familiar with. So if we have a matrix, we can break it up into it's singular values and singular vectors, meaning you break it up into its constituent directions and how much it goes in each direction. What you may not be familiar with is the idea of an epsilon rank or numerical rank. So let's say we have a million by million matrix, from some physics application. Odds are, that's real data we measured. Odds are, if you look at the rank of it, you just do the calculation, do an SVD, how many singular values are 0. It's going to be none of them. It'll be completely full rank. But if we say, in practice, I only need 6 digits or 3 digits in this problem. So I'm going to only care about singular values that are bigger than 10 to the negative third or 10 to the negative 6. That is where you're much more likely to get small rank. So for the rest of this talk, when I say low rank, I really mean approximate rank or low numerical rank. And that's kind of since the 1990s, something that's been pretty common in the literature and how these problems are solved in practice. So basically, for a matrix to be an H matrix, what that means is all the information is clustered near the diagonal. Which, if we're thinking of a physical problem, that makes sense, because if this is a discretization of a physics problem, that basically means particles close together interact more, particles far away interact less. So basically, so the diagonal blocks can be anything. They can be full rank, it doesn't really matter. But any block off of the diagonal has to have some sort of small numerical rank. And you may ask me, what is small? Really depends on your application, what you care about, but I like to think usually you want it to be around log n or smaller. Some constant times log n. So if you have a small baby example, if you have like an 1,000 by 1,000 matrix, you would want all your off diagonal blocks to have rank 10 or less for this kind of algorithm to be efficient. So we can do this. So for this, the cost of performing a matrix vector product is n log n, and we can do lots of things with this quickly, like inversion and things. The problem is this kind of matrix form is a little too simple to do things like eigenvalues. So people had to generalize it further, and that's what a lot of people have been doing in the past 10, 15 years or so. So the most popular generalization is the hierarchically semi-separable, or HSS matrix, which I'm introducing in the next slides. That's what I do my research on, and that's honestly what most people are using in the computational physics community right now. So the idea with the HSS matrix is a lot of times this information, if you're using data from a real problem, not only is it low rank off the diagonal, but the data is related to each other. Especially if you're going from some equation from quantum mechanics or electromagnetism, there's relation between the blocks, which means we can basically not just compress off the diagonal, but we can continually compress and compress and cluster and compress, and basically write the entire matrix in terms of the information on the diagonal. So basically, this huge block off the diagonal is just made up of relations between the diagonal. And how we do that mathematically is we store this tree structure. So these are all little matrices. So if your matrix is 1,000,000 by 1,000,000 or 10,000,000 by 10,000,000, these small matrices, which we call HSS generators, are maybe 1,000 by 1,000. They're small, you can store a ton of them on your computer. And basically the D ones are for diagonal. Those are your diagonal blocks. Your U and your V, those correspond to your row and column bases of your matrix. So just standard from a QR decomposition, linear algebra. And then the interesting ones are the B's, the R's, and the W's. Because those correspond to basically the relationship the blocks have to each other. And the differences between them is the R's and W's, you make them to be orthogonal, and then the B kind of is what holds the norm of the matrix. So it's a very stable construction. So this has there were a lot of different competing low rank algorithms in the past 15 years. Why this kind of won out and is now the kind of state of the art. One is it is really, really good for parallel computing. Because it's this nested basis and everything's really small and you just tree structure, you get embarrassing parallelism in a lot of cases and really low communication. That's really nice. The storage is really low, and then you can basically write everything in terms of the theory of low rank updates, which we really understand and have already done a lot of things with. So it works out pretty well. I mentioned, I don't think I've mentioned, in addition to having low rank off diagonal, for it to be truly HSS, you also have to have what's called low rank HSS block rows, which means these little strips are also low rank. And the reason you need that is it's not really heuristic, it's more mathematical. That allows you to do the nested construction. Without that, you couldn't make the off diagonal blocks from the diagonal blocks. But we found almost every low rank problem in applications has this property as well. So I said it's also very parallelizable. There's already, for linear solvers, there's already really good code online you can plug and play with. And for eigensolvers, I'm currently working on that. We should have that online by the summer. So my advisor, Jianlin Xia, is a huge person in this field, but the main groups that do this are all over the world. And it's a very international thing. I mean, there's just as many groups in Europe and Asia working on this as in the United States. I'm actually really excited because so these are probably 15 of the biggest men and women in this field, and 10 of them are all going to be at the same conference in Tokyo next week, and I'm going to be there too. So I'm really excited to talk with all of them. Okay, I will, in fairness, say HSS is not the only thing people are using. It's what I'm writing my thesis on. But for completeness, I want to quickly mention, before I get on to the individual physics problems, the two kind of competitors, so you're aware of them in case you do want to use them. So H2 is a nested basis of an H matrix. So it's kind of the inception of HSS matrices. It's an HSS with an HSS with an HSS. So it uses a lot of recursion, which means it's really fast. But it's just not very stable numerically. So if you have these huge ranks, huge matrix, this will do it faster, but it's hard to prove any accuracy if you use this kind of construction. But it's worth knowing, especially if you have a huge well-conditioned problem. Yeah?
You write inversion there?
Yeah.
Is this separate from the recursion?
Yeah, no, this is, yeah. So how this one actually works is instead of doing, so in the HSS, it's all in terms of like ULV factorizations of the matrix, and you don't explicitly do any inverses. The recursion here actually relies on inverses.
Oh, okay.
And that makes it not stable. It makes it very quick, but not as stable. And the other one you should definitely know about is the IFMM. So this is a strict geometric generalization of the fast multiple method. You can do linear solvers and things with it. This is beautiful, but you need some sort of explicit kernel function for your matrix. So in very simple physics problems, this works honestly way better than HSS. But there's so many problems these days where you're working just with data. You don't have any explicit kernel, and then this is useless. So if you know the actual function that generates your matrix, this is the way to go. I'm not going to pretend like it's not. So yeah, those are kind of the three most popular things right now. They all have their time and places. HSS, why I really like it for physics problems is it's numerically stable and it's adaptive. You don't need to know that your matrix has any sort of nice stability properties, and you can prove exactly how accurate it's going to be. And you don't need to know exactly what the rank structure looks like beforehand or the kernel function. The algorithm will find it for you, as long as it's there. Okay, so just kind of reviewing HSS matrices before I get to the actual eigenvalue algorithms and the physics problems. This was the first HSS talk I gave. Kyle Kloster, who's graduated a few years ago, was actually one that started this seminar, I think. He said, so how would I find an individual entry of an HSS matrix? And I think it's a good question to test your understanding. So let's say we have we're trying to find the 200, 201 entry of a HSS matrix that has these blocks. Basically how you would do that then is you would have to form the little sub-block, and you basically start with a row basis, end with a column basis, and you find the transistors that take you up the tree and down to the right one. So it's always about finding the path over the tree. But notice this tree is only of length log n, so that's why all the algorithms, so basically most algorithms, usually they're more complicated than just finding an n. Yep?
What do you mean by transistor?
Okay, so that is the name for these B, W, and R matrices. So those are the relationship between the blocks. That's the word you'll probably find in the literature most often is transistor. So any HSS algorithm has the general pattern of you start at the bottom of the tree, you usually wind up going up and going down, whether it's a linear system, an eigensolver, or just finding an entry, but that's not what you're usually doing. So in this case, finding an individual entry, you're doing a bunch of these really little matrix multiplications. That's what computationally you do a lot of, and the whole thing is order log squared n. So, and a lot of times, things like linear systems eigensolvers are usually n log some power of n, usually squared. But I have seen more exotic operations where it's a cubed or a fourth. Okay, so now I'm going to talk about the actual algorithm, how we solve these computational physics problems. And it's called divide and conquer. So the basic idea is that we'll start with the simplest example of an HSS matrix, which is just a tridiagonal matrix. So everything other than the main diagonals is 0. And so that basically is an HSS matrix where each of the off-diagonal blocks is just a single entry. And usually when you start an HSS matrix, you always first test it in tridiagonal matrices. So the idea here is that we can break up a tridiagonal matrix as block diagonal plus rank 1. And then we take each of those blocks T1 and T2, and we break those up as block diagonal plus rank 1. And we do this recursively over and over again until we get a diagonal matrix plus a bunch of low rank 1 updates. So that's divide, and then we conquer. And then well, very trivially, you have the eigendecomposition of a diagonal matrix is just the diagonal matrix. And then you basically build it back up, going up the tree, doing all these little rank 1 updates. And this has been known since the 90s. This is Gu and Eisenstadt's big thing. This is the workhorse of LePac and ALPA and all the main linear algebra packages. A lot of times they reduce to tridiagonal form and then do this. What me and my advisor have posited is if the matrix has nice structure, you don't need to reduce to tridiagonal form. You can just do a divide and conquer directly on the entire matrix. I will say there's one really important pre-computation step. We call it divide and conquer. It's really construct divide and conquer. In most physics problems, you're not given some pretty tridiagonal form, you're getting some ugly data. So you first have to do some pre-computation where you basically get it in HSS forms. How do I get the transistors? How do I get the row bases? The good news is this has been well studied. There's lots of free packages online that do this already. So if your matrix is something like banded, there's explicit formulas. Most likely you need some construction based on the fast multiple method, or the state of the art is all randomized. So I know Gunnar Martinson has a really good package that does this. My advisor has a good package. So you can basically do random approximations and get the row bases and the transistors. Then you divide. So it's a lot like the tridiagonal case, except you have to take little precautions to make sure your matrix keeps its HSS form. So in a tridiagonal case, you basically, to divide, you just subtract individual entries. And that implicitly keeps it tridiagonal, which is trivial. Here you have to keep it HSS, which is less trivial. So basically, at every time you divide your matrix, you have to update all of your B generators and D generators to basically keep the HSS formula, to keep the recursion valid. And so then the explicit formula for that is this updating scheme, which looks a little hairy, but it's really not too bad. It parallelizes really well, it's numerically stable. And what this basically gives us is we go from a big HSS matrix to a block diagonal matrix plus a sequence of low rank updates. They're not necessarily rank 1, they may be rank 100, rank 1,000, but they're very small compared to your million by million, billion by billion matrix. Then when we conquer, when we build that back up, so construct, divide, conquer, we basically, that is a bottom-up process, and basically at every node in the tree, we might be doing this in parallel, but basically think of visiting every single node in the tree, we have to do a rank R update to the eigenvalue problem. And how you do that is first you apply the eigenvectors from the previous level of the tree, so from the ones below it if we're moving up the tree. Then you solve a multi-rank update eigenvalue problem. I could give a whole talk on step 2, actually I did that last year. This is very tedious, but important step. Then you solve an inverse eigenvalue problem, which is a constrained optimization problem you have to solve to make sure you have stability. And then you just do some normalization. So you do this at every node of the tree until you get to the top, and then you wind up with the eigenvalues and eigenvectors of the whole thing. So are there any questions at this point? I usually go a little slower with the algorithm, but I wanted to get to a lot of physics examples, so I kind of went a little quick. But is the basic idea clear to everyone? Okay.
I just asked Jimmy, what's your final, there's a lot of steps going on, what's your final output? Because you say you don't spit out an n by n matrix.
Yeah.
So what does the final thing look like that you can then use?
So, okay, it's a little bit of spoiler alert, but I have an answer to that. Okay. So there's a really deep theorem me and my advisor proved that if you have a symmetric HSS matrix, the eigenvector matrix is itself an HSS matrix. Which, think about that for a second, it's a pretty deep property. Other than diagonal matrices, you're not going to find any other matrices that have, class matrices that have that property. It's pretty, honestly, it's pretty beautiful. And so what that means is then your output is a set of generators for the eigenvectors.
Okay. Interesting.
So the eigenvectors themselves are an HSS matrix. So we don't output an n by n array of numbers. We output some D generators, some U generators that give us the eigenvectors, and then we can So I mean, because in most applications you don't need all the eigenvectors. You either need some eigenpairs, some sets of eigenvalues and eigenvectors, or you need more likely, especially in physics, you need a projection. You need the eigenvector matrix times a vector. That's very common, especially in things like quantum mechanics. And so an HSS matrix times a vector, easy, quick. And so you basically get it as an operator. Does that answer your question?
Yeah.
Okay, that's good. I should have said that. Okay, and so representative numerical results. The slide appears 4 different times, so I'm going to kind of go through it as the things come up to different physics applications, why they're important. But the first thing I'll show is just the main result. This red line shows that the scaling, this is to get all eigenvalues and all eigenvectors of a Toeplitz matrix. That's a type of matrix that appears a lot in physics engineering problems. As an example, is n log cubed n to get all of them. Yeah, and then these are different measures of accuracy. I'm going to talk about this last one when we get to relativity a little later. But basically, the idea here is whatever tolerance you set. So that's I'm only keeping rank to 10 digits to 15 digits. That's the output you get, is that many digits of accuracy. So it's completely controllable. Whatever accuracy you want, you set it. If you're willing to get less accuracy, your algorithm will be faster. And whatever you want, you'll get. At least to that accuracy. Okay, so that's kind of the general sledgehammer, the general tool we have. Now I'm going to talk about how we can apply it to certain physics problems and how we have to tweak it in certain cases. So I'm going to start with medical imaging. This is honestly, in terms of the linear algebra, a really simple one, but it's one of our flashier ones we've gotten better results on, so I like to use it first, get people excited about our work. So in an standard MRI process, you have to do what's called regularization, which is basically all the voxels around the person will get this image, and you basically have to do some sort of smoothing to the image to make it so it's the doctor can interpret it, so the data is meaningful to the human eye. And how you do this mathematically is you basically solve an optimization problem. You have to minimize energy as it's going across your spatial dimension. And so that's not too bad, other than it's a huge problem. On these modern MRI machines, these matrices can get in the billions. I mean, it's just huge, too big to store, too big to do the computation. And it's honestly one of the reasons why MRIs take so long. And it means they're very accurate and we're able to solve a lot of people's health problems, but that's why they take so long. And really the 2 most computationally intensive steps of this regularization optimization are solving a least squares problem. I'm not going to talk about that today, but there's also a cool way to do that using HSS. And you basically you have a spectrum, your eigenvalues. You basically have to update that at every step where the diagonal of the matrix gets updated. And you have to do that in time as the person, as these pictures are being taken. So if you take the encoding matrix and you do an HSS approximation of it, you can get really high quality with a lot quicker. Obviously it's a slight approximation, so you're not getting quite as good, but it's very close. I mean, honestly, when you do this kind of thing, there's always trade-offs. You have a multi-objective optimization problem, so you decide is speed more important versus how fast, and things like the live time versus the post-computation time. But the main thing here is because it's a direct method, you avoid this iterative component, which keeps things really slow. So I want to talk about the math part of it. So if we're doing, I'll show some numerical results and some pictures of MRIs on the next slide. But look at our divide. If all we're changing is just the diagonal, when you divide, you wouldn't need these B updates, which are the most expensive part of the divide. You don't have to do it all. So basically, as cheap as doing an HSS eigen decomposition is, updating the diagonal of it is really cheap. And most eigenvalue algorithms don't have this feature. And most eigenvalue algorithms are based on some sort of power iteration, which means if you update the diagonal, you have to redo the whole thing. So you're able to reuse a lot of computation and do this really quick. How quick? So this is a paper we have from a few years ago that that showed that this line is an MRI with HSS approximations everywhere, and it's a factor of almost 100 faster. It's not quite clinically acceptable. Basically we were able to get like 3 digits of accuracy on an MRI, which to the human eye, I can't tell the difference at all. But the hospitals aren't about to start using this just because they need a little more guarantee. I mean, in my mind, this is good enough. And I mean, it's MRI 100 times faster, pretty cool, right? But we're working with some folks out at Mass General in Boston to try and tweak this so it's actually usable. So right now, this is not actually in use in hospitals, but hopefully in the future. Okay, so now a quantum mechanics application. So this is a really cool problem, comes up using things like material science and things. So the Kohn-Sham equation, this classic equation of quantum mechanics, this is actually an approximation of a density function. And if we're trying to read all the Greek there, I'll tell you that the epsilons and the phis are eigenvalues and eigenfunctions of this kind of approximate non-interacting quantum system. I'm not going to get all the quantum mechanics, but basically to solve this density, this quantum density, you need to get a bunch of eigenvalues and eigenvectors. Now, quantum mechanics, it sounds esoteric, but it's really important. I don't work on any application that doesn't have like some very obvious real-world use. So here's an example. If we look at this element, these are the eigenvalues as the spectrum. And this is true of like a lot of materials. Basically, the gap between, a lot of times these elements will have like one really pronounced gap. And that tells you a lot about the material properties of the element. This comes up a lot, like semiconductor research and a lot of finding new materials. These eigenvalues play a huge role. So this is a very active area of research in engineering. And to solve this Kohn-Sham density equation, I told you we don't often need all the eigenvectors. This is an example where you just need the functions of the eigenvectors. So basically, you need the eigenvectors times a vector. And so Nate asked what's the output, so this was kind of me getting to that. We don't form an explicit matrix. Basically, at every node of our tree, we just store a couple generators. So then to do the eigenvector matrix times a vector, you basically just do one level of the tree at a time. You do, multiply it one at a time, and that gets you mathematically equivalent, and it's numerically stable because these are orthogonal, as if you just had the whole dense eigenvector matrix. We also store a couple coefficients at every tree. So because we use the fast multiple method everywhere in this algorithm, like I said, any low rank algorithm you have, not only is it based on the FMM, I bet it will actually use the FMM in a number of places. That's how influential this algorithm is. So you need to basically store these FMM coefficients too. So that's the complete answer, is it's these generators plus these FMM coefficients at every node of the tree. And so yeah, so then we have this theorem. The output of this matrix is itself an HSS matrix. That's what our eigenvectors look like. And there's this very well-known theorem. This is Nick Hyam's statement of it in his wonderful book on functions of matrices, that if we have a symmetric matrix, which these matrices in quantum mechanics are, I know not all the matrices we're going to talk about here are symmetric, but these ones are, then the function of a matrix is just a function of its Jordan blocks. And in the symmetric case, those are just the eigenvalues. So that means is, we do this eigendecomposition, and then we just basically take the function, the Kohn-Sham density, do it on these eigenvalues, and then we just have to apply these eigenvector matrices. Usually people would avoid that because a lot of times in these semiconductor problems, this matrix would be 10 million by 10 million, or even bigger. Solving for all the eigenvalues is way too expensive. But here it's actually, we found it's faster than a lot of the existing methods people have for solving this Kohn-Sham density. And in particular, that's because this one is the storage. So the storage of the eigenvector matrix scales nearly linearly. It's n log squared n. So we only need, to get all these eigenvectors, we barely need to store n entries. That's why this is doable. Next one I'll talk about electrical networks. So this is a beautiful non-symmetric problem. Obviously you have power flowing from one node to another. It's not symmetric. So the eigenvalues of this have a lot of importance in things like controllability and basically making sure your power network is stable. So how do we get, so I told you for a symmetric matrix that the eigenvector matrix of an HSS is itself HSS. That is not true for non-symmetric matrices, which sucks. I mean, that would make things, then we could do everything. But you can, just as you can prove that the eigenvector matrices of an HSS matrix is HSS, you can just as easily prove that for a non-symmetric matrix, that's not true. It's only true for very special cases like convection diffusion problems where you have some sort of decay property. You take a general non-symmetric HSS matrix, your output is, I mean, it's not garbage, but it's fully dense. So we really can't do a divide and conquer with this. If you just need a few eigenvalues, if you need the complex eigenvalues in particular, what you have to do is something called a feast algorithm, which is basically you use tools from complex analysis and you carve out integrals across your eigenvalue space and zero in on them. I don't work on that. I have friends that do, but in a lot of physics applications, because you're working on real parameters, you don't actually need the complex eigenvalue. It's good enough just to know the singular values. And for the singular values, we do have that nice property. The singular vectors are always HSS of any HSS matrix, symmetric or not. Which makes sense because SVD is equivalent to the eigenvectors of AA transpose, right? So yeah, so this is an example from a power grid. So basically, there's a number of tricks we play to write in SVD in terms of symmetric eigenvalue problems. The main trick we play, this has been known since the 90s, but this is a cool trick if you haven't seen it, is if we have a matrix not symmetric plus a rank 1 update that's not symmetric, this is equivalent to 2 low rank symmetric updates. So how we do this is, I mean, I'll let you read the algebra, but the biggest trick that you do is you form this little artificial 2x2 matrix, and you take a Schur decomposition of it. This results due to Mingu. I can, if any of you want to see the paper, the whole thing. But then basically, you find the whole thing is equivalent to these 2 symmetric updates. So that allows you to basically, at every bit of the problem, you do your SVD as symmetric eigenvalue problems. So we use the algorithm we already have. So that's how we've been able to solve a lot of electrical network problems, is using this SVD tool. Oh yeah, can skip that for now. Okay, now on to plasma physics. This is a really cool one because plasma physics has actually motivated a lot of research in numerical linear algebra. So this is the famous Trace-Min paper by Ahmed Sama. You still work here? He's retired very recently. So this is like the algorithm for generalized eigenvalue problems. And if you actually read through this paper, he cites a few of them here, but all of his main test cases are from plasma physics. Because back in the 70s, no one knew how to solve these. Because in plasma physics, I won't get into all the theory, but you don't have AX equals lambda x, you have AX equals lambda bx. There's this other matrix there that has totally unrelated structure. And you need the generalized eigenvalues. So plasma physics actually motivated a lot of the work people have done on generalized eigenvalue problems. And to this day it does, because now we have plasma physics problems that are much bigger. The good news is you can use HSS eigenvalue decompositions on generalized eigenvalue problems. You just have to play some tricks. So basically what you do is you do a super fast eigenvalue decomposition on your B matrix, on the AX equals lambda bx. Then you basically compute what's like the square root of that matrix, is kind of what people say, which is you take one of the eigenvector matrices times the inverse square root of the eigenvalue matrix, and then you compute that times, first you have that compression step. Then you do, just for numerical reasons, you recompress it. And then you multiply that times your original eigenvalue problem. And then you compute a second eigenvalue decomposition, and that will do some back multiplication, and that will give you your original generalized eigenvalue problem. The proof of why this works is a little messy, but this is a standard technique. But what's nice is all the computations in here, it looks like a lot, but they're all linear scaling, linear scaling, linear scaling, linear scaling. It's just eigendecompositions and an eigenvector matrix times a vector. So even for generalized eigenvalue problems, which happen a lot of times, and the main one I know about is in plasma physics, but they do come out elsewhere in physics, you can still use a variant of this algorithm. Scattering theory, this is a cool one. You guys know Pei-Jin Lee in the math department. He works on a lot of these problems. I know him and my advisor. I haven't worked directly with him, but I know him and my advisor have worked on these problems. So this is, we have this incident electromagnetic wave. We're trying to calculate, the angle that it scatters and, recover information about what's inside. Some of these techniques are used in things like tomography, medical imaging, different things. So really the big seminal theory here is by the same guy, Vladimir Rock, who invented the fast multiple method, along with his student at the time, Chen, that we can basically write this numerically as what's called a Riccati equation, which is this matrix equation. And you can formulate this very quickly, just solving for all the eigenvalues of these individual matrices. The problem with this equation is it is high dimensional data. In practice, you generally only do 3-dimensional scattering, which means your data has very high ranks, which numerically means your things take too long. So to do it on something like this, you have to play a lot of tricks. That's kind of the idea I wanted to impose on you. You can't just, if you have a physics application, you can't necessarily just plug in the black box divide and conquer algorithm. You probably have to play some tricks specific to that application. So in scattering theory, the big thing you have to do is find what are called switching levels. So scattering theory is kind of a subset of what people call multi-physics. I mean, there's a lot of hierarchy of information. So in terms of the tree structure, what that means is we have to find a place where we can cut it off. And at a certain level, we're playing all the tricks, doing low rank approximations, fast multiple method, where below a certain level, it's quicker just to do standard dense linear algebra. And knowing where to do that level of the tree actually has a lot to do with the physics problem. You have to know things about the frequency of the wave and so forth. So if I know someone working this field, I'll send them a package and I'll have a parameter they can tune based on their problem, and that will allow them to do it. If you're doing scattering problems, you also have to do things like computational reuse and deflation strategies. There's basically certain tricks you have to play to get this to work as fast as for other problems because of the high dimensionality of it. So I'm running a little short on time, but I quickly want to get through a couple more. So statistical mechanics, and this is the Fermi-Dirac distribution. Very famous, and for a lot of problems, why this gets difficult is this converges to being almost, just flat, delta-looking thing. So that means it's very hard to do computations on because it's non-smooth. But this is a banded matrix in almost every real calculation, which means not only is it HSS, but it has this easy, explicit HSS form. You can do all the eigenvalues and eigenvectors explicitly. The Fermi-Dirac equation can actually be rewritten. The proof takes a minute, but I'd be happy to show it to you after we're done here. It's an optimization problem of the eigenvalues, actually a minimax problem. You minimize this optimization problem over all the different eigenvalues, and that's the same as Fermi-Dirac. But because it's banded, you use HSS, it's very fast. Astrophysics, I haven't really talked much about sparse matrices today. So the algorithm I showed you works on sparse and dense matrices just as well. But a lot of physics problems are sparse, and I want to emphasize that you can take advantage of that fact. So in astrophysics, you do a lot of these big, huge sparse streaming principal component analysis, which is just another word for SVD. And if you have a sparse matrix, basically the transistors, the R matrices, are just going to be permutation matrices. They're all just ones and zeros. So that cuts down on cost. You can do a lot more deflation, and you can really cut down on your divide cost, which basically means for if you have higher dimensional problems, it's a lot faster than it would be if your matrix wasn't sparse. The last example I want to talk about, it's kind of out there, but numerical relativity, which is a big thing. I mean, that's how all our GPSs and everything work. How people use these a lot, the most current method used most on these is called the spectral Galerkin method. If you're interested, G. Shen in the math department's an expert on this. That's basically use these high degree orthogonal polynomials to solve the PDE. But orthogonality, when you have a high degree orthogonal polynomial, obviously orthogonality is a key issue. If your matrix isn't exactly orthogonal, the whole thing falls apart. And a lot of the methods these days, that is the bottleneck they're running into. And it's stopping them from solving these big, tensor equations from relativity. But if we look at theta, which is a measure of relativity, we see that it is almost machine precision no matter what accuracy we use. And that is true of any matrix that you solve with this, because that inverse eigenvalue problem that was step 3 in the in the conquer, makes it basically what you're doing is you're admitting you can't exactly solve the eigenvalue problem. So you're basically finding a nearby eigenvalue problem that has almost exactly the right eigenvalues. What that means is your problem is perfectly stable and you get almost machine precision accuracy. All your generators are perfectly orthogonal and you get this crazy good orthogonality. And so we've had some success solving these problems from relativity because of it.
What are you calling theta there?
So that's, theta is just, it's just the orthogonality check. So if your eigenvector matrix is Q, it's just the 2 norm of Q transpose Q minus I n by n. So yeah, I mean, so this, yeah. So that you would like to go to 0, but in practice, yeah, not quite. So in future, I need to do some work so I have the parallel version's not done. I have some implementation work to make this up and running, usable by everyone. Something we still haven't really done is for non-symmetric problems, we can do the SVD. We really can't do the non-symmetric eigenvalues using this kind of method. It's something I'd like to do, haven't yet. High-dimensional eigenvalue problems, there's probably smarter ways than what we've done so far. One thing I haven't touched, a lot of interesting problems in physics, eigenvalue problems in physics, are not only generalized, they're non-linear. That we should be able to use this kind of techniques, but I haven't done it so far yet. No one's done that yet. So that would be a really good next step. And then the one thing we really are having trouble with, if you have clustered eigenvalues or extreme eigenvalues, I mean like very, really weird pathological distributions, that kind of can mess up some things in the algorithm. That's not something we've satisfactorily dealt with. And here are a few papers from myself and my advisor, and that's all I have for you today. Thank you.